In this video we'll cover Ohm's Law. Ohm's Law is the work of two people, George Simon Ohm, who did the theoretical work, and Wheatstone, who did a lot of the actual experimental work. George Simon Ohm showed that for some materials the current that flows through material is directly proportional to the potential difference across that material. Such materials are called ohmic materials. And what I've shown here is the test setup. It can be done macroscopically, or it can be done with a microscopic material in what's called a 4-point probe test for physicists and electrical engineers. In this thing you have some supply. That's a power supply like a battery where you can vary the voltage. And you put that voltage on some material. It could be wood, it could be metal, it could be ceramic, whatever. And you measure the current flowing into the material with what's called an ammeter, and you measure the voltage dropped across the material with what's called a voltmeter. And you plot those two. And if you plot those two and you find that you get a straight line, then that material is called ohmic. And this slope, which is constant, is called the resistance. However, some materials do not look like that. Some materials, for instance, might look like this. Other materials, in fact, can actually go up and even have negative slopes. They can have all sorts of interesting things. This is said to be non-ohmic, simply meaning it's not a straight line. So while people say Ohm's Law is not a law. It's an experimental verification that you get a straight line when you change the voltage and you generate a current. Now actually the way I did this, you really probably should plot the voltage on the x and the current on the y and go 1 over the slope. But I think you understand what I mean. So, like I said, Ohm's Law is not a curve, and most materials do not obey this. Only some materials. But these materials, these ohmic materials, are in fact very important materials. Resistance. Resistance is a measure of a material's opposition to the flow of charge, or opposition to current, in the material. It is the slope of our IV graph. So, in general, the material can actually be thought of having a dynamic resistance. You could think of R as equal to delta V over delta I, which is simply the slope of the graph. So you can have materials that actually have graphs that look like this. In this case, if you're over here, the slope of the tangent line, which is the slope of the graph, is actually a negative. So you have a negative resistance. This is actually very useful. These things make oscillators, a thing called tunnel diodes, and they're used actually to make microwave ovens. Over here, the slope is positive. Let me make that a different color. So over here it'd have a positive resistance. Now, in the case of ohmic materials, of fixed dimensions, the resistance is constant for a given temperature. And in that case, we can just speak about the resistance as equal to V divided by I. So in general, it's this, and it's often called the dynamic resistance. And I really should say slope of tangent line of the graph. But for ohmic materials, since it's a straight line, this slope is constant, and we simply get R is equal to V over I. Now the unit of resistance is obviously a volt divided by an amp. And an amp is a coulomb per second, and a volt happens to be a joule per coulomb, and so on and so forth. We gave it a name. We give Mr. Ohm his credit. So the unit of resistance is called the ohm, and its symbol is omega. And like I said, an ohm is a volt per amp, and then you can start going on and on as to how far down the list of SI units you want to go. Now, what's a resistor? A resistor is an electrical circuit element that transfers electrical energy into either heat or mechanical energy while obeying Ohm's law. In short, I said a capacitor was an electric piggy bank. It stores energy in the electric field. A resistor uses energy. That could be the heater in your car or the heater in a stove. It could be your television set. It could be a motor. It's something that's using up the energy, whereas the capacitor was storing the energy. The symbol for resistor is usually something that looks like that. It's kind of got a wiggly line to indicate that the going gets rough. If you look at it, it kind of looks like friction. It kind of is friction for current. And to do Ohm's law, we have to be a little careful when we draw that. So I'm going to draw two of them down here. And the question has to do with the nature of how you're going to measure this voltage and how you're going to measure the current. So let's say that that's the voltage. If I'm using up energy, the current needs to flow into the positive side. If that is the direction of your current, and this is the direction of the voltage drop, then the voltage is equal to the current times the resistance. However, if you draw your circuit diagram and choose your voltages differently, let's say I still make my voltage this way, but in this case I'm drawing positive current in the opposite direction, then my current is flowing uphill to higher potential energy. In that case, voltage is equal to minus IR. So when you put these in, the current needs to be going in the plus side and out the minus of your voltage if you're going to write it as V equal IR. Now, even if you write it this way, if you find that I is minus 3, then the voltage is going to flip. But the sign convention that you would choose when you use this form is that you're calling positive currents going into the plus side of where you define the voltage drop. Remember, only change in voltage has meaning. There are two leads. You have to tell me which way you're putting them down, the plus and minus. This is like going backwards against a force and doing the negative work. I need to know which way the displacement is. Here I need to know which way the voltage leads are. As an example of one of these problems, they ask you, what is the resistance of material if you measured 10 volts of drop when you had 4 milliamps of current flowing? So I'm going to assume that I chose my voltage here at 10 volts, and my current going into this is 4 milliamps. R is equal to V over I, 10 volts, 4 milliamps, 2.5 kilo ohms. Notice how knowing that a volt over an amp is an ohm, 1 over a milli is 1 over a thousandth, makes 1,000, which is a kilo. Knowing how to use SI units saves a lot of time. Example 2. Here I have what's called a current source that keeps constant current flowing out and through this device. All elements are in series. So they have the same current. The current of this element, this current source, is 4 milliamps. So that's also the current of this 2K resistor and the 6K ohm resistor. So looking for the voltage drop, I've got the current going into the positive side. That's what this arrow shows. Current's going plus in that direction. That goes in the plus side. So I use V is IR. Had the current been going the other direction, I would have used V is minus IR. I put in 4 milliamps. I put in 6 kilo ohms, and I get 24 volts.